purpose of this video is to discuss the concept of molecular polarity. And this is different from individual bond polarity that we've been looking at. But what we're going to see in this video is that molecular polarity is dictated both by shape as well as individual bond polarity. So this is the final column that you're filling in that packet on building molecules and drawing Lewis structures and looking at shape. So to fill in this final column, we need to first learn about molecular. So we are familiar with the idea that water is a polar molecule. But why? What does this mean for water to be polar? Well, I've drawn a picture of the shape of water here. It's a bent or angular shape. Here I have a complete Lewis dot structure. Remember, one of the common mistakes is students forget about these lone pairs when they draw Lewis dot structures. Make sure you always show the full number of valence electrons that each atom contributes to the Lewis structure. In this case, water has to have 8 electrons, so you can't forget those lone pairs. And what I've done here is I've shown the individual bonds that we find in water. Now, there are 2 of these bonds. There's an oxygen to hydrogen bond that occurs twice. So I've pulled it out just once, and what I want to do is diagram this individual bond. So on your packet, you've done this already, but you should find the hydrogen gets the partial positive charge, and the oxygen gets the partial negative charge. Again, that's because oxygen is more electronegative, and so it is going to be pulling these 2 electrons closer to itself, leaving hydrogen electron deficient at a partial positive and oxygen electron rich at a partial negative. Now, there's another way to diagram bond polarities. In addition to the partial negative, partial positive system, we could also use a system that uses an arrow. And the arrow points toward the more electronegative elements. And then we put a little tick mark on the side of the more, or the side of the less electronegative element, in this case, hydrogen. And that tick mark just kind of reminds us that the hydrogen end has a partial positive end, and the electrons being pulled toward the oxygen at more partial negative. So again, this is another way that we can diagram polar bonds. We could use this arrow notation, or you could always use the partial negative, partial positive delta symbols. Okay, so either the delta notation or the arrow notation from now on is just fine. So let's get back to our original question. Water is a polar molecule, but why? Well, these bonds, these polar bonds, are found inside the molecule itself. And what happens, I've redrawn the molecule here, is the oxygen is pulling the electrons in this bond toward itself. So I'll represent that by this arrow here. And oxygen's also pulling these electrons toward itself. I'll represent that by a second arrow. So this arrow represents these polar bonds, or what are also called dipoles. So a dipole is another word for a polar bond. And what happens in water is that these 2 dipoles pull up at an angle toward water, and they result in what's called a net or sum dipole. And the net or sum dipole would look like this. I'm actually going to draw it over here to make the picture a little clearer. So you have the oxygen, draw that really light. We have the hydrogen of water. We have the other hydrogen over here. These arrows represent the individual bonds, dipoles, the pulling of electrons toward that oxygen atom. But then I'm going to say that, or show you, that these 2 arrows would result in a total or net or sum dipole that would look like this. So there's an overall net motion of the electrons diagonally upward to the left. This is called a vector sum. If you're interested in looking that up, it's more of a physics topic. But if you're interested in vector sums and how we can take 2 poles or 2 forces and sum them up to a net force, you can look, you can Google that search if you'd like, that term if you'd like. But I think we could agree that the arrow pointing up here and pointing up here, or to the left here, if we were to add them up, if we were to find a sort of sum or total, it would be a diagonal up to the left. What that means for water as a whole is that water has this diagonal up to the left net pull of electrons. And as a whole molecule, that means the molecule is now kind of split in half, where the left side has an overall partial negative charge, and the right side has an overall partial positive charge. And these overall partial negatives and positives are what we refer to as the molecular dipoles, or the molecular polarity. Molecular polarity is the sum of the individual dipoles adding up to a net molecular dipole. Another way to show this is that if I draw the water again over here, here's my hydrogens. Water has an overall imbalance of charge on its surface, where we have the top left would have like an overall partial negative, the bottom right an overall partial positive. Now remember, the overall molecule, any overall molecule is neutral, right? Molecules are neutral, unless they're polyatomic ions, but if you're speaking of a molecule, the overall molecule is neutral. Water is a neutral molecule, but it's polar because it has an imbalance of these individual bonds dipoles. So again, what is molecular polarity? It results from individual bond dipoles summing up or adding up to a net molecular dipole. What we see in nature is that the water molecule, or any polar molecule, has an imbalance of charge on it. It's overall neutral, but it is showing an imbalance where one side shows a partial negative, one side shows a partial positive. But the question is, do individual dipoles always do this? Do polar bonds within a molecule always sum up to a net molecular dipole? And the answer is no. This doesn't always happen. Just because you have polar bonds doesn't mean you have a polar molecule. And that's where shape comes into play. And we will be exploring that in our next video.